talk of the day is by Javier Gonzalez, who is at Amazon in Cambridge, and Javier has been helping to organize the summer school for many years now. He's going to be talking about Bayesian optimization, and thank you for coming, Javier.
Thanks. No, thanks for the invite. It's always great to come here to Sheffield. Okay, so I've heard, and I know this because we also have been doing this in the past, that you have been going to the brewery as a social event, right? So how many of you have already been in the brewery? It's the Kellam Island Brewery, right? Okay, so for those of you who haven't been there yet, what happens when you go to the brewery is that you try some beer, you try some pie, you have some fun, you connect to other people. But there is something that I find very interesting as well, is that some people there making beer show you how is the process of making beer, right? So they take you to the facility and they show you how basically with 5 ingredients, which are water, sugar, yeast, hops, and grain, you can make all sorts of type of ales, right? So if you go to that brewery, they have particular recipes to brew the beers that they sell, right? Have you tried to ask them how they came up with those recipes? You should. So the first thing we are going to do in this tutorial, we're going to be talking about Bayesian optimization, but before that, we are going to go through this exercise. I'm going to try to make this tutorial very interactive, so I'm going to make you work a little bit. So the first thing I want you to think before we start talking about Bayesian optimization is, imagine that tomorrow you start working for the Kellam Island Brewery, right? And the first thing that you have to do is to come up with a new recipe for beer that you want to sell, right? So I'm going to give you 2 minutes. I want you to talk to the people on your right, on your left, and think about 2 main issues that you may have when producing a new recipe for beer. The first one is, which are the constraints that you have, which are the challenges. And the second thing I want you to think about a general pipeline, not just for producing one type of beer, one type of recipe, but for producing more on the future. So just think that tomorrow you start working on the Kellam Island Brewery, and that they ask you to think of a pipeline to come up with new recipes for beer. What would you do? I'm going to give you a couple of minutes to think about that, and then we'll come back. We'll discuss it. Okay, so I hope you came up with some ideas about how to come up with your new recipe for beer. So yeah.
Quick question. He told me like it takes 4 or 5 days to reach basically the result.
Yeah.
So it means like if you want to test many possibilities of like increasing sugar or whatever, every time you have to wait for like 4 or 5 days.
Exactly. And that's one of the main issues that you will have. You have to come up with a Exactly, with a new recipe, right? Every time you try a new recipe, you have to wait for 5 years, for 5 days until the whole, not 5 years, until the whole process has been completed to do what with it. So what do we do?
Taste.
To taste? Who tastes the beer? How do we check how good the beer is?
Put it out. Tasting it above.
So we sell it. We
I don't know, like having a panel of like
Yeah.
people, experts or whatever, who kind of like when you do the wine and they like sip and spit and
Right. So we have, in a way, so we have to define which is our objective function here, right? Which is something that is not clear because we can think about asking a panel of experts. We can think about trying the beer ourselves. We can try about running an experiment. We start selling some beer in some neighborhood of Sheffield and see how that goes, right? So first we have the problem of defining the objective function in this problem, right? Because I guess now you all agree that this is an optimization problem. We want to optimize the recipe for a particular purpose, right? The second one is how do we actually test new recipes in the facility, in the brewery, right? That because this is going to take a lot of time. Any other issues?
Well, I guess we need an informative prior to put all the knowledge that the brewery has accumulated over the past,
Yeah.
so that we can achieve our
Exactly. So a way to go would be, well, if this brewery has been selling this type of beer for a few years, maybe we can go for something similar, right? And that's something sensible, right? How do you think? So these are potential issues, and all these are going to come up later. And which are how do you imagine a pipeline for producing different type of beers? How do you imagine something like this happening? And how do you imagine machine learning helping you to build new recipes for beers?
a black box with knobs.
A black box, yeah?
I would imagine it like a reinforcement learning kind of algorithm, meaning like you test and you modify as you go.
Uh-huh.
You test, you try, people give you some feedback, and then you modify through this feedback. So the new recipe, you test it, and you have other, adapted kind of.
That's very good intuition, and actually something that we can discuss later is that actually Bayesian optimization is some form of reinforcement learning without a state, right? So exactly, we're going to be thinking on these lines on how to use reinforcement learning or sequential decision-making type of algorithms to optimize our objective function that in this case is to maximize the satisfaction of a group of people drinking our beer, right? Okay, so keep this example in mind. So now I'm gonna start the slides, the presentation. So this is the goal of the tutorial, right? So we talk about beer brewing. I brought here this sentence from Alfred North Whitehead. Civilization advances by extending the number of important operations which we can perform without thinking of them, right? So if you think about making beer, those operations are which recipes should we be testing, right? To come up with new interesting recipes. So and we're interested in automation. In machine learning, we do a lot of automation. And the main application areas of Bayesian optimization are automatic design of physical experiments, which is what we have been discussing already, and automatic model configuration, which means that we have a model or a family of model or a very complex data science pipeline, and what we want to do is to optimize decisions, to decide how many hidden layers and how many layers we should have in our neural network, or should we use algorithm A or algorithm B to solve a particular problem given a data set, right? So these are the two main applications of Bayesian optimization. So if you think about a data science pipeline, you can have your own idea of what doing data science means and how a pipeline like this looks. But you can think about it like something that involves some data collection, right? We extract some features, we do some modeling, right? We were saying before, well, we don't really know how the recipe maps to how people are going to like the beer that we have, right? So we can have some intuition about that, but we'll need to do some modeling to match those two things. And then this may happen or not, but in the problems we are going to be talking about, we are going to have some model, we are going to interpret some results, and there's going to be some feedback loop that will require doing this several times, right? When you do this, when you think about this pipeline, there are many decisions that you need to make here, right? You have to make decisions about what data you collect, how do you design your experiment to collect data with a particular goal in mind, right? You need to decide how do you handle the data, what data processing pipeline you use. You have to decide how you use the model. You have to optimize your model, right? And then you have to come back in this outer loop. All these decisions, or most of them, can actually be represented as optimization problems. How many of you have solved an optimization problem recently? Okay, all of you. Okay, in how many cases, when solving that optimization problem, you don't have an explicit form of the function that you wanted to optimize? Some of them. Okay, so the cases that we are going to study here today are optimization problems in which we have some well-behaved function. Typically, by well-behaved, we assume that the function is continuous and in some cases differentiable. Is defined on some subset of RD, although we'll see how we can relax this assumption. This is the general formulation of the problem. And the goal is to find the minimum, the global minimum of the function in that set, right? Extra assumptions that we are going to make about the problem is that f is explicitly unknown and multimodal. So when you are optimizing a piece of computer code, when you are calibrating a complex simulator, when you're optimizing a recipe for beer, you don't have an explicit form of f as you had when you were kids and you started to find the minimum and maximum of functions by taking the derivative, making that equal to 0, and computing the critical points, right? So we don't know that. We know that we have access to the function that we want to optimize, but we only have access to it through a finite and very expensive, a finite number of evaluations, right? So there is a budget or cost component involved in what we are doing here. And we are going to assume that f is expensive to evaluate, right? As we were saying before, if I want to try a new recipe, I have to wait for 5 days until I have the answer, right? Okay, so this is the setup. Any question so far? No? It's clear. Okay, cool. So an example that I was saying before, I'm bringing here an example of automatic model configuration, which is very popular, which is how you select the best architecture for your neural network, right? So you don't really know beforehand if you add another layer in the neural network, how that maps to the accuracy that you get with the neural network, right? But you have a computer code that you can run to check that. You can optimize weight penalties, learning rates, whether you do dropout or not, et cetera, et cetera. Okay. Another thing is that this is just an example that I took from one of the papers in the literature from Nando de Freitas. It's like, how do you optimize going from A to B in a path when you have some constraints and you have a simulator to do that. Okay, so you can think now about, so I just mentioned a couple of specific examples, but I'm sure that now you have in mind your own problems and your own examples about this. And you can think about problems in robotics, right? When you want to optimize the picking of a robot arm. You can think about planning. You can think about optimizing hardware and software, optimizing compilers, industrial design, or you can think about dealing with intractable likelihoods, or brewing beer as well, right? Okay, so so we were saying, don't look at the slide. I know you can see some results. So imagine that I give you this problem, right? So we have a unidimensional function that we want to optimize in this interval over here, and we don't know anything about the function. We know that satisfies some regularity conditions, right? How do you optimize this? So the first thing that you do is something like what you mentioned before. Is like, well, if what I'm optimizing here is I'm maximizing the number of customers that are going to buy my beer or the satisfaction of my customers, I'm going to try just ask to the people in the brewery because they have been in this business for many years, so they can tell me what can I do. So if I have trained many neural networks and I know that a particular architecture works well, I'm going to try something similar for my new problem, right? That's valid. How many of you have done something like that before? Right? Yeah, that's a sensible approach. But what we're trying to do here is to formalize that a bit more, right? Okay, the second thing that you can do is like, well, you can actually go and do grid search, right? So if I know that I can evaluate the function I'm optimizing here, and I know I'm optimizing it in this interval, I can just do some grid over here, right? I compute the values of the function and say, look, if I'm looking for the maximum sits in this point over here. Fine, that's okay. That's people do grid search, but that's generally a bad idea. And the reason why it's a bad idea is because remember this assumption that we were making about our problem, that is that our function is very expensive to evaluate. So if we want to use this approach to come up with a recipe to brew beer, the problem is that if we are optimizing on a parameter space that has 5 parameters, that is the type of water, the type of sugar, the type of yeast, the hops, and the grain, then what happens is this property here. If the function that we are optimizing is Lipschitz continuous, and by Lipschitz continuous, I mean that I can basically, for 2 points, x and x prime in the domain I'm looking at, I can bound the output given some constants, some positive constants, times some distance between the input, right? So things don't get out of control, basically, and I can control that. So if I have a function that is Lipschitz continuous, and I know that this is the optimum of my function, and I want to solve this problem with arbitrary precision, right? The problem that I have already in dimensionality 5 is that if I want to solve this problem with precision 0.01, which is okay, this is the number of evaluations that I need, right? So doing grid search doesn't really scale well. It may be okay, you have 1 dimension and the function is not very expensive, but definitely this is something that is not going to work if we want to come up with a good recipe for the beer, right? More ideas apart from grid search. What can you do?
Random search.
Random search. Why random search is a better idea than grid search? So I give you a budget of 100 points, and you are solving a problem of dimensionality 2, right? And you can either do grid search in a grid of 10 times 10, or you can just allocate 10 random points in the input domain. Why doing random is better than doing grid search? Any idea?
If you don't find an optimum, it's easier to add new points.
If you don't find an optimum, what do you mean by that?
So if you're not convinced by the results, it's easier to add new points by sampling randomly. You cannot always extend the grids.
Right. Okay, because the grid has a particular structure, right? And random, you cannot actually add more points, right?
Does the space is filled better with random points?
We will discuss that a little bit more. Sorry?
You do less iteration.
So you have 100 points. You can either do grid search or do random search.
No, I mean, if you do random search, you would have less iteration than a grid with 100 by 100. Like you just try.
Something you can do with random search is that you can trivially parallelize random search, right? So the grid, you have to put it there in one shot. Random search, you can always parallelize more, which is something like what you're saying.
Is it to do with high dimensions, lots of the mass that exists in the shell, and if you're going in grid search, you're penetrating the entire volume, but random search might keep you all around the shell of a problem?
You can come up with arguments in that direction. A way of looking into that as well is like, well, if I'm doing grid search over here, right? So imagine that the function that I have is built or has the property that the variables involved in the value of a function have different weight, right? Or I have some type of additive component, right? So imagine that I can assume that the function that I'm optimizing has somehow this shape, right? x1, f1, x1, f2, x2. So there is some additiveness there, which is an assumption that is reasonable sometimes, right? So what happens if you have something like this, in this dimension over here, if this is x1 and this is x2, in this dimension over here, I'm only collecting 10 points, right? In this dimension over here, I'm only collecting 10 points. But overall, I'm collecting 100 of them. If what I'm doing is random search, if I have some additive structure, in each projection, I'm already collecting 100 points, which is much more informative than doing random search, right? That's an argument. So the first thing that you have to learn from this tutorial is to stop using grid search, right? So you have a problem, better use random search than doing grid search, unless you have a way to do some structured experimental design, right?
But aren't Sobol sequences better than purely random generation?
It depends. They both have pros and cons. They can be better because Sobol sequences induce a negative correlation between the points because they have this repulsion property. We are going to be talking a bit about determinantal point processes, right? But we are not comparing random search with Sobol sequences. We are comparing it with purely grid search, right? Done in a brute force manner. Yeah, we can talk later about that.
What about gradient descent if we have like the derivative?
Uh-huh.
Can we do that?
But we don't know anything about the function yet.
Yeah.
Yeah, we can use that. We can use that later. But
You learn more about the interaction between the different parameters.
correct. Yeah. So you can do grid search or random search across different dimensions, different subsets. You can split your input space. You can do all that. Yeah. More questions? No. Yeah.
Surely you want to be able to control for one of the variables, but if you start adding randomly, whilst you get a wider more diversity in your samples, you lose that ability, surely.
Mm-hmm.
So my question is there a trade-off there? You're no longer able to control that number?
So you will see how with Bayesian optimization, you somehow automatically are going to be able to control that. With Bayesian optimization, we are going to see how we are going to be doing a bit of random search at the beginning of the optimization, and then we are going to do more structural search as soon as we learn more about the problem that we are trying to solve. So we will come to something like that. Okay? So we have analyzed intuition, we have analyzed grid search, we have analyzed random search. The question is, can we do better, right? So now I have a problem for you, right? So we have, imagine that we have a function that we want to optimize, and we want to minimize this function that is defined in the interval 0, 1. Do you know that the function is Lipschitz continuous, so no crazy jumps happen in the function? And do you know that we have 4 exact evaluation of the function that we are looking at, right? And actually the situation looks like this, right? So this is the input interval. This is the parameter that I'm optimizing. I want to minimize this function. And now I want to ask you the question of where is the minimum of f, given the information that I have just given you? And the second one is, if you could take another evaluation, where would you take it, right? And now I want you again to discuss for a couple of minutes the answer to these 2 questions. So again, talk to your colleagues, and we will discuss later.
Is the range between 0 and 1? Between 0 and 1?
Yeah?
It's between 0 and 1. You can't get mine. You can't pick.
It's only between 0 and 1. It's only between 0 and 1. So where is the minimum of f? Where do you take a next evaluation?
If I was drawing a curve for these things, I could. It's like very simple.
talking about GPs again. So I would sample right between the sample. We're talking about how much is the variance. Because there, if you think about the GP, and there, the uncertainty. Yeah, we're already looking at this like a GP. It's awesome.
We'll get there. We'll get there.
Because if it's a longer length scale, then we would say, oh yeah, it's going to be around points. Like our power is very strong around points. Yeah.
But if you sample where the uncertainty is highest, it might not give you any more information. But it'll give you a better estimate.
Okay.
Yeah, exactly. This gives you a lot of information that you're able to allow.
Okay. So you had some time to think about this problem. The situation is a bit dramatic, right? It's like we don't really know much about what's going on with the function. We only have 4 evaluations. We have some previous knowledge about how it may look, right? So any brave volunteer to answer these 2 questions. So where is the minimum of f? Who knows? Who knows? If you have to guess, if you have to put your money on a location where you think the minimum of s is, what would you do? 0.6. Here? You mean right here or close to this one?
Somewhere to the left of that.
Somewhere to the left, somewhere over here. So, okay. How many of you think that the minimum is in this range over here? How many of you? Okay? More or less?
That's where I would check.
That's okay. So how many of you think that the minimum is actually right here?
Well, if I had to put my money on something, I would put it there.
You will put it here. That's a reasonable assumption, right? It's the only thing that we have observed. That is the current best that we have observed. Okay.
What do you mean? Because, I mean, if we just choose a point, then our probability to find exactly the minimum is basically 0, right?
We are going to come to the probability now.
This is a continuous.
Yeah?
continuous axis.
Okay. Okay. Now
We need more information about the sampling.
you need more. Okay.
Something was done.
More ideas about the minimum of f
Between 0.3 and 0.9.
between 0.3 and 0.9.
Not strong prior.
Okay. Okay. So, okay, so we have some idea of where the minimum of f is. Obviously, we don't know exactly where the minimum we cannot know that. But so what if I tell you, okay, I give you another evaluation, where would you get it?
Between
Well-
second and third.
Between somewhere over here
Yeah,
Right.
somewhere in the middle.
on this side? So there is no full agreement here where we will get the next evaluation, right? So before I ask you, so do you think the minimum is somewhere over here? And some people said yes. So I guess what happened is like, you imagine that the function that we are optimizing is something like this, right? We know that the function goes through the points, so it's not making any big jump. So it's doing something like this. Okay, so the minimum can be over here or over here, right? So a few people answer this, right? So what I'm doing here is like, I'm just drawing here some samples that you imagine, right? So I imagine that the 3 people in the first row imagine these 3 functions going through the points which are reasonable and agree with the information that we have about the problem. And what I'm plotting here is the histogram of the minimum of these functions, right?
But you didn't tell us the Lipschitz constant or how it relates
No, I didn't.
with the x-axis.
No, I didn't, but you have some intuition about what that value is because you know how much the function is changing here given this distance, and you know that the points are equally distant from each other. I didn't say what the Lipschitz constant is, right? I'm making you think, right? Okay, 3 curves, histogram of the distribution of the minimum. Actually, there is a lot of people in this room, right? So I guess that everyone imagine a different function going through the points, right? So I keep drawing functions that were in your mind, right? I'm using you as a generative model of potential functions that agree with the problem that we have. And what I'm doing here is computing the histogram of the minimum of those functions that were in your mind, right? Okay, so we can keep asking people. We ask more people, and we ask more people and more people. We ask the entire University of Sheffield. We ask Sheffield, right? Now we have many functions that agree with the information that we have, and now we have a distribution or histogram over the minimum of those functions that we had over there, right? So what is going on? What happens now is like, oh, imagine that we have infinitely many samples of infinitely many people attending the GPSS this year, and we have some probability distribution over the minimum of this function that we are trying to optimize. just by looking at some way of generating samples that agree with the information that we had. That was part of the Lipschitz continuity, that was part of the interval when we are optimizing the function, and you have combined that with some data that we have collected from the actual process, right? So what happened here, right? So by just reasoning in the Bayesian way about the process that links this parameter to the output of the function, we have constructed an object that allows us to reason about the object of interest for us, which is the minimum of the function, right? So we have built a probability measure over f, and we have translated what that means to build a probability measure over a property of that f, right? Which is the distribution of the minimum. So now if you think about the problem that we want to solve, we want to find the minimum of f in this interval that we are looking at. So what we have done is to build a surrogate model that maps inputs and outputs in the function. We have defined some utility function to collect new points. That's what we are going to do. We are going to use this object to decide where we are going to collect new evaluations, right? If you know that this is the probability distribution of the minimum, and now I ask you, where do you think the minimum is? What would you say? You would say, in the mode of this distribution, right? And now if I ask you, what would you do to collect new points? You could do things like, well, I'm going to collect a point that maximally reduces the entropy of the distribution, that makes it as more informative as possible, right? So now you have the distribution of the minimum. You can do whatever you want with it, right? So if you do that, what you are doing is you are transforming an optimization problem in a decision problem. The original optimization problem that you wanted to solve, finding the minimum of f, you have transformed it in a sequential decision problem of deciding where to evaluate the function in the next iteration, right? And what you have done by generating these samples about the function is to transform every one of those decision problems in a problem of inference, in a problem of quantifying the distribution over the object that you're interested about, which is all we always do, right? So we have optimization. We transform optimization, global optimization, as sequential decision making, right? A decision problem. And each one of those decision problems, we are going to solve them using probabilistic inference and Gaussian processes, right? Any questions so far? So clear? Okay. So now you can ask yourself the question of, well, in this tutorial, we're interested on optimizing the function, right? Or finding the minimum. But what happens if I'm interested on learning more about the function itself, right? Or what if I'm interested on computing the integral of the function, right? Or the location of maximum gradient of the function. Can we do that? Absolutely. You can do that using very similar reasoning to the one that we use just to optimize the function. The difference is that your target goal when collecting the new evaluations will be different. We were saying, well, once we have constructed the distribution of the minimum, if we want to collect a new point, we will do it in a way that maximally reduces the entropy of that distribution, right? If you wanted to know more about the integral of the function that you are looking at, you will need to collect points that maximally reduce the distribution over the integral, right? If what you want to do is just to know about f, and that's what you typically do in active learning or experimental design, you need to come up with something that reflects that objective with your design, that objective with the sequential decisions that you are making, right? So we'll see how active learning just does exploration, right? Just explore the space, which is related to the experimental design and this type of strategies that we were talking at the beginning. And we will see how, when you do Bayesian optimization, you combine exploration and exploitation. You explore to learn more about the function itself, and you exploit once you know about that particular property that you are trying to learn. Okay, so basically with our examples, we built already the standard Bayesian optimization loop. that is due to Mockus, 1978. So these ideas have been there for many years. And we'll discuss why people are using them a lot of in many applications now. So what do? You choose your prior measure over the space of possible f. You know how to do that. You are in a Gaussian process summer school. I don't even have to tell you that you can use LGP for this. This is not the only thing that you can use. You can use a Bayesian neural network. You can use a random forest. We like using GPs because how easy it is to embed a structure into the covariance function, right? And for other properties that GPs have and that are very interesting to use in practice. So we define some previous measure. We observe some data. So basically, we compute a posterior measure given the data that we have. And once we have the measure over f, what we are going to do is we are going to build an acquisition or loss function that is going to represent our design goal, right? So this is something that we haven't done yet, and mainly the rest of the talk is going to be about how do we build these acquisition functions so we can actually drive the search and find the optimum as soon as possible, right, with the minimum amount of evaluation. Once we have used this acquisition to collect more data, you augment the data, and you repeat the process over and over unless you don't have any more budget, right? And that's it. This is what Bayesian optimization does.
So, how are we in practice supposed to choose this prior measure? So, for example, our brewery scenario, what covariance function I'm supposed to have, what parametric family I'm supposed to have, something like this.
That's an excellent question, and I would say that people have done a lot of research on new acquisitions and loss functions, but I think if you really want to make Bayesian optimization practical, you need to think about the problem. So people used to say, well, you use Bayesian optimization as a black box optimization method, which means that whatever model I use is going to be fine for me to find the optimum, right? That's not true. You need to embed into the modeling as much as you know about the problem. If you are solving a problem in dimension 2, in a domain that is not very large, maybe things will work. If you really want to use this for a serious application, you need to sit with an expert, build your covariance function, and use it in the optimization process. So this transforms a bit what you do with Bayesian optimization in a modeling problem, right? And these two components, one that is the model and the other one that is the acquisition, you need to pay attention to both of them. And you have been talking about many different type of models during the summer school. That's why I'm focusing here. But having the right model for the right application is key to make this work in practice. Right?
What may be the pipeline for this? For example, for our scenario with the brewery, how would I begin something like that?
For your brewery, so something you could do is to start with a few recipes. Something you would need to do in the brewery probably is to run parallel evaluations, right? Every time you try a recipe, you need to spend 5 days. But maybe something they can do is they can try 10 recipes in parallel, right? So you have to come up with an acquisition function to do that. You need to embed information into the system, right? It's up to you how to do that. You can embed the information by prior knowledge, and if you don't have that prior knowledge, you need to acquire more evaluations. If that's the scenario, you need to find strategies to do that efficiently, right? It really depends on the problem. Questions? Yeah. Yeah. So when you have integer values, so that comes to the case in which you have to optimize. We will see later how, given the data and given your model, you build your acquisition function, and now you still have to optimize this acquisition function, right? And you have integer values, you are going to have a problem because solving an integer optimization problem is going to be hard. But the reason why you can do it is because you know everything about this acquisition function, right? So you can use any standard optimization method to deal with this. So you can go to the biggest book in global optimization that you have, in which you have gradients, in which you have integer programming, in which you have everything you know about the optimization, you can drop it here, which is not something that you can drop in the original problem because you didn't even know the function, right? So the key here is the surrogate model or the emulator that is transforming this optimization problem that is intractable. We don't even know what is going on. We have 4 evaluations. We know nothing about this into something, to a sequence of problems that are tractable and that you can solve with the optimization that you know. In case of having integer values, so you are going to be doing the lab with GPyOp, we do something very naive, which is just to approximate to the closest. So we solve in a continuous space and you approximate to the closest integer value, which is a wrong thing to do. You can do that in a much better way, but it does the work approximately. Okay.
I'm wondering about the GP part of this, because if you're trying to set up, like you said, integrate prior knowledge, say into the covariance function, how smooth this thing would vary. In high-dimensional spaces, that's going to be hard to gather intuition, and I wouldn't want to necessarily take like a previous random sampling run, because that's based on, say, my biased beliefs of the range of the hyperparameters, which that would be introduced into my GP. So how would you?
How would you deal with that? So there are different directions that you can take there. One is think about the structure of your function. So people have come up with methods of solving high-dimensional optimization problems when you have additive structure in the function. You have additive structure, then you're already imposing a lot into the function that you are optimizing, right? Another direction that you can take is the direction of transfer learning, right? It's like if I have solved already a similar problem to the one I'm looking at now, I'm going to extract whatever I have in the model that I use for solving that optimization problem and warm start the model that I'm going to use for this one. That would be another strategy. That's very sensible in cases in which you don't have a structural or physical knowledge about your problem, about the surrogate model. You have no idea of how one thing relates to the other. So in the case of the brewery, you probably wouldn't have that. But you can go and talk to the brewery next corner and try to extract that information, the kind of transfer to the problem that you have now. No more questions? Okay, so 2 elements in Bayesian optimization. One is the model. The other one is the acquisition function. So just one slide about the model. So this is a GP. You know, these are samples from my GP. This is for the sample that we were considering before. You know, you have your model. You have a closed form of the posterior that we can use. You know that this is nice because because of the properties of the GP, when we constrain it to a finite set of points, all this is multivariate Gaussian, and we like working with multivariate Gaussians because we can do everything with them with linear algebra, right? So one of the key aspects of Bayesian optimization, and probably you have heard about this before, and not only Bayesian optimization, you also have this when you have active learning or when you do RL, is the exploration exploitation trade-off, right? So I really like this example. So when you go to a restaurant and you maximize the utility in which you are selecting, right? You can either explore new things that you don't know if you are going to like or not, or you can go for your favorite food, right? So that's kind of an intuitive way of representing the exploration exploitation. So when we explore, we are going to try to collect actually the most informative points because they are going to reduce my uncertainty. If I don't know if I like the quesadillas or not, the best thing I can do to figure it out is just to try, right? So if I'm looking into an optimization problem and I have no idea how my objective function looks in a particular region in the domain space, the best thing I can do is just go and sample, right, and collect a point. If I'm pretty sure that I want to deliver my result now and that this is going to be my last evaluation, you should exploit, right? You should go for something that you know is going to work in the experiment that you are running. So this is a nice paper. It's a NeurIPS paper, 2013, and they relate different standard optimization methods to the way humans actually solve optimization problems, the way you did it in the example that I gave to you. And they saw that in one-dimensional examples, humans are actually pretty good finding the optimum just by selecting the points, and they are much better than any other out-of-the-shelf algorithm, right? And this is because of our capacity of encapsulating the data that we observe with the prior knowledge that we have about the function, something that you did in the example, right? Obviously, they did it in only one dimension because they wanted to solve the problems to humans, right? So we know exploration, exploitation. We want to balance between learning more and making sure that we make evaluations that are going to work, right? So this is what we're going to do now is we're going to visit some of the most popular acquisition functions in the literature, and one of them is the GP upper confidence bound. And the reason why this is popular is because you can derive a lot of theoretical warranties with it. So imagine this is the function that you are optimizing. This is your GP. What you do is to say, well, I'm going to collect my next evaluation, but maximizing the minus the mean of the GP, and minus because I'm minimizing, not maximizing, plus some parameters, some positive parameters, plus the standard deviation of the GP, right? So this, if you see the shape of this object over here is an upper bound of the function that I have, and if I can upper bound the function, I can upper bound the optimum, and I can derive theory for that. And interestingly, this acquisition function makes very explicit the trade-off between exploration and exploitation, right? Because if you want to exploit what you already know about your function of interest, you just use the mean, right? Let's exploit what we believe the shape of the function is. If what you want to do is to explore, what you do is you use the variance, right? So if you are familiar with active learning, if you drop this term over here and you only use the variance and you maximize it, you are exactly doing experimental design and active learning, right? If you have this term over here, you are balancing exploration and exploitation. In this particular acquisition function, this beta term balances how much you explore versus how much you exploit, which is kind of the key in the design of any acquisition function in Bayesian optimization, right? So here, so this is just a copy and paste of the main theorem of this paper, 2010, in which what they do is they bound the regret that you get through the optimization. The regret, I saw it before, but I didn't comment on it. Is basically the difference between the accumulated difference between the optimum and what you have been observed in your sequence of points. So this is the theorem. So it requires noiseless evaluation. So as soon as you have noisy objective function, this is not the theory is not going to hold, but you can do a lot in the theoretical domain with it. Okay. So another acquisition function, probably the most popular one, is the expected improvement. Yeah, question.
Can you go back?
Yeah.
What's on the right-hand side? RT lower and equal.
This is the regret at time t. This is a bound that depends on the number of evaluations, the dimension, the number of evaluations and the dimension that you have.
So two things: number of evaluations and the dimension.
Yeah, exactly. Yeah.
Beta was chosen to minimize the path, right?
Yes. And it's dynamic, so it changes in each iteration. Yep.
One more question. So I'm just thinking a bit about the philosophical implication of this approach. So what we're saying initially is that our function is high dimensional, so we don't know anything about it.
We are not saying it's high dimensional. It can be. In principle, this type of methods are proven to work well when the dimensionality is not very, very large. So when we use them to optimize a neural network, we don't optimize the weights. We optimize the hyperparameters of the neural network.
Okay, but let's say it has some dimensionality.
Yeah.
And optimizing it is hard, and therefore we transfer this thing to evaluate an acquisition function, which is basically some sort of probability distribution where you think your maximum is. But then you're still left with optimizing this function.
Correct.
So we transferred from optimizing the original function
Correct.
to another function that has the same dimensionality.
Correct.
So what have we gained?
What you have gained is that in this second optimization problem that you have, you know everything about your function. It's very cheap to evaluate. You know gradients, and you can evaluate it for free everywhere in the input domain, which is something you cannot do in the original optimization problem.
Right, because we have a model.
Exactly.
Okay, fair enough.
Is the model what allows you to do that jump. It's true that you are transforming a impossible optimization problem in a very hard and complex optimization problem. That's what you are doing, right? But you are gaining something on the way by using the model. That's an excellent question. Yeah. Yep.
Another one about the previous slide. So what's our assumptions on the underlying function f?
It's Lipschitz continuity.
Lipschitz, okay.
Yeah. More questions? No? Okay. So expected improvement. This is the I would say the most used acquisition function. What do we do? So this is our model. This is our GP. We have 4 evaluations. This is the current best. This is the best evaluation that we have observed, right? So what we do is we define the expectation with respect to the model of improving with respect to the current best, right? So we say, well, in expectation, how much are we going to improve our current best if we evaluate our function here? Probably nothing, according to the model, right? How much, in average, we are going to improve over our current best if we evaluate somewhere over here? Probably a lot, right? And then I compute this object, and then I maximize it, and I select the next evaluation that I want, right? Which is sensible. It's not, at the beginning when we built the example, we were thinking about the probability distribution over the minimum and collecting the new point in a location that makes that probability distribution to be as spiky as possible, right? This is a different approach that is based on the expectation on doing better than we have already done. In this particular case, we can write this acquisition function in a way in which we have gradients and we can optimize. And when you optimize these acquisition functions, obviously you are doing this in a, let's say, 5 input dimensional domain. You are going to run many instances where you are going to initialize many optimizers because this acquisition is going to be multimodal, and you need to make sure that you hit the global optimum there, which may not happen, but you hope for the best, right? It's the most used in acquisition. It's explicit for Gaussian posterior, so you can compute it in closed form when you have a Gaussian process. If you change your belief model of the function, you will need to recompute this. Yeah, and that's pretty much it. So I have a question for you. So when we think about this acquisition function, and you think about how you define it, which is basically the expectation of improving given our current best, look at this. So you are using the current best evaluation that you have, right? Do you see any issue by using this value here, right? Which in this case will be this one over here. So in which cases this acquisition function is going to break? And we have mentioned some of these cases before.
Noisy, with like noise observation.
Exactly. So what happens if this is noisy, right? Then I'm not sure if this is really my current best or not, right? So what you will need to do is to reintegrate out the expected improvement with respect to the current best that you have. Yep. Okay. Thompson sampling. Another thing you can do is to say, well, look, I'm going just to draw a sample from my Gaussian process. I'm going to minimize it because we're minimizing. I take minus the sample and maximize for consistency with the rest of the acquisitions. I take the optimum, in this case, this point over here, right? And I take this as my next evaluation, right? So there is a difference between this acquisition function and previous acquisition functions that I have mentioned, which is that this is a stochastic acquisition function. If you draw a different sample from the GP, you are going to have a different location, right? But it still works very well in practice, and you see how it naturally encourages exploration and exploitation, right? So in regions where you have larger uncertainty, pretty much anything can happen with the function. So you are going to be willing to explore there, and the exploitation comes because you are going to go through the carbon-based location that you have already observed, right? Questions?
Do you have any sort of theoretical guarantees or like how it performs compared to the other ones?
The GP upper confidence bound is pretty much the only acquisition with theoretical guarantees. The rest are heuristics.
Also, just one question: how would you optimize a sample from a GP?
That's a very good question. How would you even generate a sample from the GP? So how do you think I have generated this sample over here? What have I done to make this plot?
Draw 1,000 points.
Okay, so I have drawn 1,000 plot points here, right? And then I just connected them in a line. Can I do that in practice? Is that something that I can do in practice? Right? Because this is like doing the grid search for the acquisition, right? And what we know is that this makes sense because we can use optimization methods to optimize this acquisition function. So isn't that a problem? If we do Thompson sampling just by using the properties, the Gaussian properties of the GP, and we do this in a grid? Yes, that's a problem. And that's a problem when you have large dimensions, right? And you have the same problem that you had when using grid search, right? Something you can do, and this is something you can only do in a restrictive number of cases, is to use the Thompson sampling in a continuous setting, right? So what you can do is you can approximate samples from the GP using Wagner theorem that basically tells you that you can approximate samples by Fourier components, right? So what you are doing is f of x is your GP. This is a stochastic process that you are going to represent by some basis of functions, right? Where these basis of functions are going to be Fourier components. You are going to approximate some of these basis of functions and draw samples by drawing from the distribution of these weights. This is the intuition behind it, right? And then you can draw these samples. The samples are going to be better the more terms you have in this approximation, but at least you can use them, and you can use anything that you know from optimization to get the optimum of them, right? The last acquisition function that we are going to discuss today is entropy search, which is pretty much the idea that I described at the beginning. So when you have a full characterization of the distribution over the minimum, you collect the point that in expectation maximize the entropy, right? Interestingly, when you do Thompson sampling, when you generate a sample from the GP and you get the optimum, that is a sample from the distribution over the minimum, right? So something you can do is, if you can generate many samples from the GP using Thompson sampling, you optimize them all, you already have an approximation of the distribution over the minimum that you can use to compute this acquisition function, which is what we did in our experiment, right? Okay, so yeah, this is a formalization of what I just described. Okay, questions so far? No? Okay, so this is a figure from this paper. It's 2013. It's a bit old-fashioned now, but the message that I want to say is that there is no single acquisition function that always works better than the other in all the examples that you can look at. If someone is telling you, look, I have designed this new acquisition function, it's the best acquisition function that you can possibly use, it's going to work the best everywhere you try, is lying. That never happens. And the reason why that happens is that, as I said before, acquisition functions are a balance between exploration and exploitation, and different problems require to handle that balance in a different way. If you have a very simple problem, you have a convex problem, you can exploit more because of the properties of it. If you have a very complex problem, you will need to spend more time on exploring than exploiting. And that's not warranted beforehand given the acquisition that you use. And now you are questioning, how do I choose my acquisition function? more or less? Or how do I balance exploration and exploitation? There are ways of doing that. There are acquisition functions that work better than others in general. Something you can do to balance exploration and exploitation is to think non-myopically about the problems. All these acquisition functions select the newest evaluation, assuming that it's going to be the last one, right? What you really need to do is, assuming that you have a budget to solve your problem, try to think how your next evaluation is going to affect the future evaluations that you are going to compute in the future and do the rollout. But that requires to solve some Bellman equation that's hard and complicated. If we have time, we will discuss a bit more about that.
So given you're choosing an acquisition function, so you have your acquisition function and it operates solely on your sort of model, right?
Yeah.
Does this mean that does it make any sense to sub in and out different acquisition functions at different points of the optimization? Can that work, or is that going to be a really bad idea?
Yeah, people have tried that. So you can do a partition in your space, and you can use different. You can have a hierarchical model. You can use different models in the different partitions. You can do ensembles of acquisition functions as well, and you can reweight them depending on how they are doing. People have tried it. It works well in some cases. Yeah. So by default, if you look into most standard Bayesian optimization libraries, what most people use by default is the Matter 5.2 kernel with expected improvement. And I think people use that because some know-how that have been collected that is not a bad default option, but there is no specific reason to do it. Right? More questions? Oh. Okay. So these are the typical figures that you see in Bayesian optimization papers. Okay, so let's see how this works, right? So this is actually the function that I showed you at the beginning, the one that we were optimizing, the one for which I give you 4 evaluations. Now I just give you one, and this is the model that we have. So it has this uncertainty over here, this uncertainty over there. The horizontal yellow line is representing the level of my carbon best evaluation, and the black line is representing the mean of the model, and this is the standard deviation, right? So this is expected improvement, and this is expected improvement normalized between 0 and 1 for visualization purposes. So now what happens is that the expected improvement is telling me, look, because of the uncertainty and the carbon model that you have, anywhere here or anywhere here is good for you to collect new points, right? They are all equivalent, right? So what we are doing is just go to the extreme. We're going to collect 1 point here. We update our model, right? And now we re-optimize the acquisition function again. Here or here will be the same. We are going to the extreme. This is a bit arbitrary at the beginning, but I have selected the points this way because I want to illustrate you something already. If you see here, we are minimizing, right? So what you observe is that here we have observed a very high value of the objective. Here we have observed a value of the objective that is closer to the current best that we have. And you see the intelligence that the acquisition function is putting already here is saying, look, because here things are very high, in this region you don't need to evaluate anymore, right? Forget and discard this region over here. I'm not so sure about what is happening here because this seems to be almost as good as this, right? So keep an eye on what happened in this region. I optimize the acquisition function. I collect my new point there. It's like, okay, so we reduce uncertainty. So we now come here. We don't know anything about this region. So we collect a new evaluation, right? Look what is happening. What is interesting is that the first 4 evaluations look a bit like some grid search, right? What we are doing is some experimental design. In this first exploration phase, what the method is doing is just collapse uncertainty in the different regions of the space. We are gaining global knowledge about the shape of the function, right? And as soon as we have done that, now this is very interesting, right? Because now we get, now that we evaluate here, and this point is much better compared to any of the other points that we have selected before, now the acquisition function is discarding most of the space in which we're optimizing, right? So we don't need to collect more evaluations here or here. The acquisition is telling us that the optimum is not there, assuming that the model is right. We collect a few more evaluations, and there we go. And we find the optimum, right?
So I can imagine all kinds of problems when we are arriving closer and closer to really optimum.
Yeah.
So, for example, this function is very picky now, and gradient-based optimization will be difficult.
Yeah.
So, what's the usual approach? Do we just leave it to some local optimization, or what?
You do all sorts of hacks. So you need to solve this optimization problem, and you need to come up with way of hitting this mass here. You are completely right. You can, and that can be a problem, right? That can be a problem. No one talks about this, but this is some of the deepest secrets implemented in libraries that do Bayesian optimization, right? Something you can do here and that works well in practice is to initialize your optimizer from the points that you have already observed. When you are at the end of the optimization, if you have done well, you expect the optimum to be close to something that you have already observed. So you expect the acquisition function to have accumulated some mass in that region. So you expect that if you start optimizing from here, you are going to hit somewhere there, right? Something you can do is, well, I'm going to build because evaluating this acquisition function is very cheap, right? It's very, very cheap, and I can do it in parallel, right? So you can run a massive grid search over here, right? Or a random search, compute the values of the acquisition, and to start your optimizer from something that is high, right? So if you run a massive grid search here, and you hit this value here, and you hit all these values here, you start your local optimizer over here, right? That's a problem.
One more. So, and what's with the problem that maybe length scale, which was fitted by all those faraway points, will be not very descriptive of this local nature of the
Yeah.
function. So what are the facts for this?
So in that case, you can either have a hierarchical model that handles global and local length scales, or something you can do is, as soon as you know, you can imagine that you are here, right? So you can say, well, if this is expected improvement, right? But imagine that you had the entropy search, and this was the distribution of the minimum. What you can use is a level set computed from that probability distribution to restart another optimization in a subset of the input domain in which you can adapt your length scale that is just in that region.
So another problem, yes.
Yeah. Yeah, people have tried different things. All
Hierarchical models like deep Gaussian processes.
you can use deep Gaussian processes as well, and we have used that. The problem with deep Gaussian processes is, well, you need more data to get something that is meaningful out of the model that with a standard GP. And because you do approximations, the uncertainty that you get out of it may not be as significant for your problem as you expect. But people have used it as well for optimization. It comes with its own price, let's say.
Maybe my question is a bit silly, but
No silly questions.
this means that you assume you already have the point, and then you find the point to retraining. Why you didn't train those points at the beginning?
Say again?
I mean, because you use the Bayesian optimization to find some point, you want to train it.
Uh-huh.
Why you didn't use the point training at the beginning?
So you mean that you don't? So when you mean points, you mean?
Yeah, you already have this data at your hand. Why you didn't use this data training the model at the beginning?
You could have.
Just one question.
Yeah.
Another question, because you assume you find the really elegant model. When you will stop to explore your stuff? When you stop?
So, so you see what you normally do when you do Bayesian optimization. You can do it this way, starting from the first evaluation and moving ahead and collecting more and more. In practice, what you typically do is you simply start with some random design or with some Sobol sequence. Instead of doing Bayesian optimization in each single iteration, what you do is to start with a bunch of points that you draw randomly in the input domain. You feed your model there, and you start collecting new evaluations. Because you know that your model is going to do something like that anyway, right? So that's the first question. The second one was, I don't remember what.
When you will stop
You stop. So typically, you either you assume that you have a finite budget, so you run your algorithm until some finite horizon, or here you can come up with a heuristic that says, well, if I start collecting points that are very close, my algorithm has converged, right? Here you already collected points in this region, so you compute the distance between the last two evaluations, and that distance is smaller than some tolerance that you fixed beforehand. You can stop. Mark?
How sort of efficiently you collect these evaluations will naturally depend on how good your model is, right? And so does it make sense to optimize your hyperparameters in between evaluations? Can you do that? Is that like?
You need to do that. You need to do that, and you can even do better than that, which is instead of optimizing the hyperparameters, something you can do is you put some hyperpriors over the hyperparameters and you integrate them out. And that typically works better, especially at the beginning of the optimization, right? More questions? Yep.
Something that I'm thinking of is that as an output we get not really an optimum, but this beautiful picture of our surrogate model.
Mm-hmm.
So
no, you get an optimum.
Optimum as well, of
Yeah.
course, but we get really more.
Mm-hmm.
So can we use this, for example, to find robust optimums? So not like the picky ones, but the ones in which neighborhood is also like minimal or maximal, something like that. And somebody does that.
So what do you exactly mean by robust? So you mean an optimum in which, I recently read a paper actually that was doing that. I don't remember. I can try to remember which paper that was. And they were looking for optimum with certain property. That is, I want an optimum in a place where I'm not going to drop very fast from there, right? Yeah, you can do that. I've seen something like that recently.
You said something very interesting that the acquisition function assumes every time that your next point is going to be the last point. However, in reality, of course, you have some sort of budget. So are there any established techniques that actually look into the future and make some sort of planning?
Yes, there are a couple of algorithms that do that. We have worked on that in the past, and I have a couple of slides. How long do I have? So I have 15 more minutes. I will visit that in a couple of minutes later. More questions? Right. So we have completed the loop. So we discussed the models and the properties of the model that we need to do to Bayesian optimization. We have discussed the main acquisition functions, and we have discussed the main philosophy and the main idea behind what Bayesian optimization does, right? And as we discussed this before, actually. So all we are doing when we do Bayesian optimization is we are transforming this original optimization problem that is unsolvable in principle into a sequence of optimization problems that we know how to solve using standard optimization techniques, right? And the reason why that's the case is because we know everything about the acquisition function, this alpha acquisition function. We know everything about the expected improvement. We know gradients. It's very cheap to compute. We can parallelize evaluation. We can run multiple optimizers to find the maximum, which is something that we cannot do in this original problem, right? Okay. So secrets of Bayesian optimization. The model matters a lot. We discussed this already with the beer example. Optimizing the acquisition can be hard. We all have also discussed this, and you need to be aware of the dimension. If you use standard methods because of the properties of the GPs, if you go to high dimension, you need to incorporate more structure into the optimization process. That structure may come from more structure in the model using some semi-mechanistic model that reflects the domain application in which you are applying the method, or it may come because you simply find ways of collecting more points, like doing things like parallelizing the way you collect the evaluations. So I have another 10 minutes, 12 minutes. So I just want to discuss these 3 points briefly, and then I will discuss a bit the non-myopic idea. So what do you do with the hyperparameters of the model, how to select points to initialize the model, and how to optimize the acquisition function. So this is what we discussed. So imagine that these are posterior samples from different hyperpriors for different values of the hyperparameters, right? So one thing you can do is to integrate them up, as we mentioned before. This is going to make the optimization method to be more robust, especially at the beginning. When you collect enough information, it's going to be pretty much the same, optimizing the hyperparameters or integrating that with respect to the distribution of the hyperparameters given the data. It's going to be quite similar. Something you can do as well, using the same type of idea, is, so imagine that you want to optimize in parallel. So imagine that you have several cores, right? What you want to do is to say, well, I have 5 cores in which I can evaluate the performance of a model for different hyperparameters. I start evaluating the models in the 5 cores, and after an hour, one of the evaluations is already finished, right? And I want to keep this core occupied with another evaluation, right? But I'm still evaluating 4 of them. So something you can do is decide on the next point that you are going to send to this core by integrating out in the values in which you are currently evaluating and doing things asynchronously in parallel. That's another idea that has been exploited that comes here because is a way of integrating out some things that are pending on or that depends on the distribution of the hyperparameters that you have. How to initialize the model? We've also discussed a lot of this. So we have discussed about how to do random search, how to do grid search. There are these beautiful processes that are called determinantal point processes that work very well when you use them to initialize your models in Bayesian optimization. So these are point process, and what they do is they are probability measures over subsets, right? So imagine that you have a set x1 xn, and you want to define a process that assign a probability of sampling simultaneously several points of the set that you have, right? So they are called determinantal point process because what they do is they define the probability of finding 2 points together in the sample that you get proportional to the determinant of the kernel associated to those 2 points. So imagine that you have a set of points x1, xn, and you use you define a kernel that can be an RBF kernel, for instance. So you compute it. Basically, what you do is to say, well, the probability of selecting element y and j in the same sample is proportional to the determinant of the minor corresponding to the entries of points y and j in the covariance matrix. When you do that, what you see is that the value of this minor is the product of k y j j minus this product over here. This means that the more similar the points are, the less probability they have of appearing in the same subsample. So this is a process that encourages and induces a negative correlation between the points in the sample, right? And encourage some diversity in the points, right? So this is just an example for visualization purposes. So imagine that you generate points independently, right? Uniform sampling. You get this. These points are independent. They don't know the other points exist, right? So you can have effects like having 2 points very close, which may not be the best if you want to explore at the beginning of the optimization because you want to collect information. If you use a determinantal point process, you are imposing this repulsion in the points that you collect, so you have a much better coverage of the space, right? So this, if you think about it, is something between what you do when you grid search and random sample, right? So if you have the additive property that we were discussing before, you have as many points per dimension as you have in the sample, but still you have a pretty good coverage in the space that you are looking at. These are beautiful processes. If you look into the literature, there are nice examples in nature that follow this type of point processes. So you look at how trees grow in a field. they follow a determinantal point process because they use some of the resources around them and they don't let other trees to grow in a neighborhood, right?
Just a question, it's more of a general GP one,
Yeah.
but it seems related to, say, doing hyperparameter optimization.
Yeah.
If you have mixed hyperparameters, those that take discrete values and those that take continuous,
Yeah.
how do you choose a kernel that would work with, say, this or even any?
So you either design a kernel, you have a categorical variable, for instance, you need to do some sort of one-hot encoding and treat everything as continuous and then re-optimize. That goes into the detail of the problem and how you want to treat each variable. So you can treat the variables at the level of the model and build a covariance function for them, or you can push the problem to the optimization, the acquisition function, assuming everything is continuous and handle it there. But it's a tricky problem. People are still looking into it.
So for this process, right, I mean, it's kind of like what you described is try to distribute
Yeah.
points, right? But does this process allow it to exploit at certain stage?
It doesn't. So that's why we are talking about it as a way of initializing the model, not as a way as doing the optimization. Some people have tried to use these processes for Bayesian optimization to build batches, which is, these processes have a very interesting property, which is like when you look into this. So basically, if you imagine that each point in your set is a vector, right? This kernel matrix, it's capturing the correlation and the covariance between those. So if you have a point that is x1 and you have a point that is x2, right? Basically, the more similar these 2 points are, the less likely is they are going to be in the same sample and the other way around. So you have actually 2 ways of improving the probability of two points being in the same sample. One is if you could make them more orthogonal to each other, right? Or you can increase the norm of the point and increase the value of the determinant, right? So a beautiful interpretation of determinantal point processes is a geometric interpretation in which you can look into them as a way of balancing quality of the points that you have in the sample versus diversity of the points that you get because of their similarity in the kernel. So you could potentially design a covariance function for the DPP that encourages some quality term for some of the points in the sample. Right? People have done that. Okay, optimization. I don't want to stop here a lot. As we have discussed, you need to use standard optimization methods to optimize the acquisition function, and that can be tricky, but it is doable. Something I want to talk about. So I think I'm going to talk about. I have a few things here. I think I'm going to talk about the non-myopic search. So we have been talking about about exploitation as one of the key elements to design acquisition functions, right? And we briefly mentioned that a way of balancing exploration and exploitation is actually thinking non-myopically about the problem, right? The intuition behind this is like, if you remember the restaurant example in which we had to decide what food we were going to get, we wanted to explore or exploit. Well, that decision will change if you know how many times you are going to be able to go to the same restaurant, right? So if you live in a city and you know that you are going to be there for 10 more years, you don't really mind exploring new things in the restaurant because you can always come back and get something that you know you like, right? But if it's the last time you're going to go to the restaurant, what you really want to do is to get something that you want. So the smaller is the budget that you have, the more exploitation you should do in the next evaluation, right? So imagine this problem here, right? This is very simple, but imagine that you are optimizing a function in this interval over here, right? And I tell you that you have one evaluation to optimize the function, right? Many algorithms will do this, will collect the point in the middle, right? And now, if once you have collected this point, I tell you that you have another evaluation that you can take, what you will do is to subdivide this interval over here, right? If from the very beginning you know that figure is not here. If from the very beginning you know that you have two evaluations, you will never collect the two evaluations like that, right? You will collect them equally with the same distance in the space, right? So this is how you should take into account what you do now for the future policy that you are going to be using by taking into account the budget that you have for solving the problem, right? So this is just the intuition, and this is something that we did a few years ago already. So imagine that you are writing your paper and you have a deadline in 24 hours, and you are training your model and you are optimizing it, right? What you want to do is to tell your optimizer that you only have 24 hours to train your model and to get the best out of the optimization process after that time, right? So we had this paper that was called Glasses. It was Glasses relieving the myopia of Bayesian optimization. Global optimization will look ahead through stochastic simulation and expected loss search. And we did some experiments and we saw that it was working nicely. So this is a nice direction. Many other things, applications, we have done things like synthetic gene design with Bayesian optimization. Unfortunately, I'm now separating you from lunch, so I'm just going to wrap up. Some take-home messages. We have been discussing about many different things. Bayesian optimization is a way of first encoding your belief and using those beliefs to making optimal decisions with some target in mind. In this particular presentation, we have been optimizing the function, but tomorrow Maren is going to be talking about how to use similar ideas instead of for computing the optimum of f for computing the integral of f, right? Key elements, the model and the acquisition. Now there is still research on acquisition functions in Bayesian optimization, but I think the most interesting stuff now is happening at the level of the model and how you encode your beliefs about your problem there. Acquisition functions, remember they explore, they balance exploration and exploitation, and that's key to solve your problem. So that's pretty much it. It's 12:30, so if you have any questions, I'm happy to take. Question? I mean, you have been asking a lot, and if you want to go for lunch, you can go for lunch, and I'm going to be around here today and tomorrow, so. Yeah.
Questions.
Yeah.
The first was, you said something about Thompson sampling being